1 second. Okay. Do you see the screen
Yes,
and the
everything is
pointer?
fine. Yes, everything
Perfect.
is fine. Okay, then we can continue with the second talk of today, which is the talk by Jesus Huertas from IFT Madrid, who will talk about topological couplings in holographic and observable branes from string theory. Please, Jesus, you may start.
Thank you, Adriana, and thank you all of the organizers for giving me the opportunity to present my work here. I'm Jesus from the IFT, and I will talk about these two recent papers with my supervisor, Ángel Uranga, and one with Iñaki García Echevarría. And more or less, the topic is topological couplings in holographic end-of-the-world branes from string theory. So, the plan for this talk. In the first part, I will give you like an introduction of these configurations of end-of-the-world branes in ADS5 cross S5 that are the D3s ending on fibers. They are like the Cobordism to nothing of the end-of-the-world branes. In part 1, I will explain like the SymTFT funds, the first article, that realize like a boundary for a SymTFT. There are the SymTFT of a field theory with a boundary. And in the last part, I will break some supersymmetry, locally some supersymmetry on this end-of-the-world brane, and we will see that some global gauge anomalies will appear, and we will see the cancellation of them. So any urgent question during the talk, you can ask. If not, later. First part, introduction. Let me start with the Cobordism conjecture, that is a Swampland conjecture. Many of you for sure know it, that states that the Cobordism classes of any solution of quantum gravity have to be trivial. So in particular, there must exist a domain wall that interpolates between every two consistent quantum gravity, as the Cobordism class is the same, it's the trivial one. And moreover, there must exist like a configuration that interpolates between your quantum gravity to nothing, to the is an end-of-the-world brane. No? So what is this Cobordism to nothing in ADS5 cross S5? Well, if we take some D3 branes, you have here 16 supercharges, 4-dimensional and equal 4 in its work volume. Then you can put some 5 branes and end these D3s on the 5 branes. The Ds NS5 and D5 will eat the 5-4 flags of the D3s, and then your configuration will end. You have the branes at these directions. They perform this symmetry, and this precise configuration breaks half of the supercharges, and you have like a 3-dimension n equal 4. Okay. This realizes like a CFT4 ending on a boundary conformal field theory 3. Your field theory has a boundary. This boundary conformal field theory 3 was studied by Gayotto and Witten some years ago. Let's now go to the gravity dual. No, we are trying to see like Cobordism to nothing in quantum gravity. So what is the gravity dual? The gravity dual was studied by these people is ADS5 times S5 ending on an ADS4 end-of-the-world brane. I will explain you. The spacetime symmetries, well, these are the symmetries. This in spacetime translate to ADS4 times 2 spheres times a Riemann surface, a 2-dimensional Riemann surface. Now, if you look at the branes, you will see that this brane grabs one of these 2 spheres and the other brane the other. And you have an ADS4 that are formed by this 3-dimension and the radial one. And this is the 10-dimensional metric. Everything is fiber along this Riemann surface sigma. These other people realized that we can have configurations where asymptotically you have ADS5 cross S5, because the ADS4 combined with the R and the 2 spheres with the angular direction to form an S5. And in the other side, you have a smooth ending of spacetime. You have here ADS4 times R6, like a smooth cap. And what else? Yes, the fibrils, important. The fibrils are located at the boundary of this sigma, this Riemann surface, and they are located at this point, they grab ADS4 and one of the 2 spheres. And the other branes, the NS5, for example, grab the other. And looking at the metric, what we will have is like an ADS5 throat And then we get to this bug where the spikes are the location. This is the supergravity solution, are the location of the fibrils, and then nothing. It's a cobordism between from ADS5 cross S5 to nothing, to a boundary. Now, the key point, this will be using this configuration a lot in the paper, is to reduce to five dimensions. No? In 5 dimensions, in point carré coordinates, means that you have here the holographic boundary and you slice ADS5 in ADS4 branes. No? So this will be like the radius R. And then when you ADS4 slices, asymptotically, you have ADS5, but then you arrive to the position of the fibrils and then to the end of the spacetime. This was studied in this paper that we have from last year, and these are our end of the world brane configurations. Notice here, like as I told you, the five branes eat the 5-4 flux of the D3s, and the flux is being reduced until it goes to 0, and then the 5 sphere can shrink to 0. And also, I will not talk about this in this talk, but this realize also like a fuzzy Karp-Randall brane, all this end of the world brane configuration. Okay, let's go to our first part, where we will study these SymTFT fans. So, first of all, what is a SymTFT? Imagine that you have here your field theory, the dimensional field theory, you have your gapless fields, your symmetries, and then you can have like some topological symmetries. The SymTFT is a useful construction to study these topological symmetries. No? You extend your theory, gluing it to a D+1 dimensional bulk symmetric topological field theory, and then you add a topological boundary. These topological fields, you put the boundary conditions of this field in the topological boundary, and these boundary conditions select you, like for example, the gauge group structure or your physical boundary. You can study these symmetries using this construction. Then you can glue together the two boundaries, stack them, and you have your field theory that you have before. But now you have the information about these topological conditions. Now, what is the SymTFT in ADS-CFT? These authors gave us like a prescription to compute this. And for case theory with an holographic dual, for example, ADS5 cross S5, there exists a systematic way to extract the SymTFT. You dimensionally reduce over the base of the transverse dimension cone. No? Like for our case, ADS5 cross S5, this amounts to compactify the 5 sphere and get to the 5-dimensional theory. No. And what happens here in 10 dimensions? You have this coupling on your branes. When you compactify on the 5 sphere, you integrate the F5 along on this 5 sphere, and then you get n, the number of brane, the number of 5-4 flux, and then you get this Chern-Simons coupling on your 5-dimensional theory that relates B2 and C2, these two forms. So in our configuration before, what we will have is like here in the physical boundary, we have our 4-dimensional n = 4 super jam mills. And here in the bulk, we will have this topological coupling, and we will impose boundary conditions on these B2 and C2 fields. And we will see that they are not independent, but they live on a set n class, and there are some relation between them. And they give you like the global form for the gauge group on the CFT4. They also are like background fields for the 1-4 symmetries in the field theory. Okay, this is the SymTFT in ADS-CFT, in the usual. But now we can ask ourselves the question. We are working with this end of the world brane that are dual to this CFT4 ending on a boundary conformal field theory 3. So what is the SymTFT of this configuration? Can we write a SymTFT for this type of thing? To do this, we apply this procedure that we just review, compactifying the compact sphere, and we get our previous construction. We got this point carré, in this sense, this point carré coordinates these 5 branes that spans ADS4 until the space disappears at nothing. This will be like the SymTFT. Why? Because at each of these regions, we have this coupling. No? Here is n, is the usual one, But then at this point is at this region, at this wedge is M1 because some of the Pfeiffer flash has been eaten by the 5 branes. Here is M2, and until you put a lot of branes until it disappears completely, and this will be like a trivial SymTFT. The last one. We called it like SymTFT fun, no? Because it resembles like the Spanish funs at the end. And this is like the main topic of this talk. Okay, we have at each SymTFT, at each SymTFT region, we have this symmetry set in where the two forms are defined, but they are different, no? So we can ask ourselves the question, how they glue? We have topological theories with different content and that are together. How can they glue? And what we have is that in the 5 branes, we have non-topological field theories on this region. So we will see that there are U1 defined on this junction on the SymTFT that allows these two different groups to talk among each other. Okay, before going to that, let's review the symmetry construction of these authors. This is the same as SymTFT. They have the topological boundary, but then they have two different physical boundaries that doesn't talk to each other, that shares the same topological boundary. And they intersect these two branches on a junction theory where they show that there is a U1 defined. Our construction is similar, but in some points different. No, this is what we have. This will be like the fun, but with the explicit D5 here. This will be like the SymTFT that lives on the 5 branes, no? On the work volume of the 5 branes. The topological boundary, instead of being here, we have that is shared among the branches, is here, and the physical boundary is there. No? Another interesting point is that for all the branches, they have a physical boundary that is 3-dimensional instead of 4-dimensional because they are defined on wedges. And for the 5 branes, they have a physical boundary here. And then in the paper, we show that indeed we have the set N and set M on the given by the 5-4 fluxes, and we saw that there is a U1 at this junction that allows these two symmetries to talk. Okay, to finish this section about the SymTFT funds, let us review one topological operator that is the D5 baryons. We have ADS5 times S5. We can wrap a D5 on the S5, so it is localized on ADS5, well, it expands on time. And Witten in the 98 showed that this baryon has to have n string attached to be consistent. No? In the holographic boundary, these strings are seen as quarks, so they are like a combination of n quarks that is a baryon. And he shows that they have this set n symmetry. We can now introduce the baryon here on this part of the SymTFT. It has n string attached because the symmetry is set n. But if we try to cross it, then the symmetry is set M. So how this works? This works because when we cross the baryon on the 5 branes, there are like the D3 brane charge localized on the 5 branes that are eaten. And when we cross the baryon via Hanani-Witten-like effect, you create P fundamental strings that combines with some of the strings of the baryons and cancel them. So now the baryon has only M string attached to it. So our theory is consistent. So we show how explicitly all these symmetries are defined on these branches. So take home message for this section is that we define the SymTFT for a theory with a case theory with a boundary, and we saw how the different operators transform and behave on this configuration, and it's well defined. Okay. Let's go to part 2. Another word branes with less SUSY. We will try here to break SUSY, and we will see what what new phenomena appear. Okay, we start again with the D3s with 16 supercharges. We put the same D5 and NS5 that breaks to 8 supercharges, and we want to further break SUSY. To do this, we introduce an orientifold 5 plane that shares only direction 9 with D5. This will break the supersymmetry to 4 supercharges locally. So we will have 3-dimension n equal 2 supersymmetry. These are the previous direction of the brane. The O5 shares 4 and 5 with the NS5 and 9 with the D5. We can also introduce another type of branes that are rotated D5 and NS5. They will break also to 4 supercharges, but it won't be like locally with like a global breaking of supersymmetry, and they don't introduce anomaly, so it is not as interesting as the orientifold. So the orientifold. Another interesting thing about the orientifold that will be very useful is like the action, the values of the action is not free, but due to the orientifold can only take 2 values, 0 or 1/2. So on the first place, let us review the C0, the action equals 0 case. We have the NS5, we have the orientifold 5. These are the direction. They only are different on 6 and 9, that are these ones. And because the orientifold is crossed by an NS5, the orientifold will split into the orientifold 5 minus, and the other side will have orientifold 5 plus that has Ramon charge plus 2. So we now have a mismatch of Ramon charge. This has to be solved by putting 4 D5 semi-infinity, D5 on top of the orientifold 5. The name, sorry, I didn't explain, these are called orientifold fork configuration, are called fork because they resemble in some sense a fork. And these are the configuration that we will use in this section. Okay, we can add an arbitrary number of branes. They have to be even because of the orientifold projection. And in the orientifold 5 plus, they are projected, the U1 gauge symmetry on the 5 branes, they are projected to USP n. And on the other side, in the orientifold 5 minus, the UN symmetry is projected to SON symmetry. That's about C0 equals 0. Let's go to C0 equal 1/2, where the interesting thing will happen. Okay, due to supersymmetry, a PQ brane goes in the direction 9 and 6 given by this relation. It's given by this, was explained by these authors. So in the case of C0 equals 0, an NS5 brane, that is a 0, 1 brane, extends along 9, along 0, 1. That is like the straight line, the vertical line that we are used to. But in the case C0 equals 1/2, now the NS5 extends along this line, 1/2, 1. We can put GS to 1. This for C0 equals 1/2 before the orientifold. If we introduce now an orientifold, what we will have, as the orientifold has to reflect the NS5 brane, we will have that the image of the PQ brane has to be, due to the axis flip, has to be an P plus Q minus Q brane. In particular, if we do our previous fork configuration for an NS5 brane, the image of this NS5 brane is a 1 minus 1 brane. So it is like a PQ web, also for these authors. The thing is that now we have one Ramon charge already, given by this orientifold image. So we only need to introduce 3 D5 branes on top of the orientifold 5 minus. And this is crucial for the anomaly thing, because now we have an odd number of D5 that we will flavor. So let's use an example. This discussion is general, but I want to use an example to make it more clear. Well, I mean, it's general in the sense that we can introduce a lot of D5 branes, no? Here in even numbers and here in odd numbers. So let's introduce 2 D5 branes here and 5 D5 branes on the other side. Well, we will have an USP2 here and here an SO5. So in the intersection, in the five-dimensional interface, we have a lot of open strings going between the five branes, and the spectrum of these open strings will be a half hypermultiplet transforming on the bifundamental 2-5, bifundamental of USP2 and SO5. So from the point of view of the USP2, there are an odd number of flavors that are the ones on the fundamental of SO5, an odd number of flavors transforming and then its fundamental, the fundamental of USP2 on this five-dimensional interface between the two orientifolds. This is an odd number of fermions then. So then we will have an anomaly. Why? Because this odd number of fermions plus that the fifth homotopy group of USP2n is not trivial, is set 2, was shown in this paper, then we have this global Gibbs anomaly that within the typical within SU2 anomaly. That is an anomaly when you have a gauge group and you make a large gauge transformation, your theory is anomalous. And this is given because we have an odd number of fermions and a non-trivial homotopy group. So we have this anomaly. This anomaly has to be cancelled somehow because our theory is a string theory construction and has to be consistent. So the resolution is that there should be an anomaly inflow from this 6-dimensional bulk to the 5-dimensional boundary that are here. Why? A easy way to see that this anomaly inflow exists is to introduce another NS5 in the other side with another number of d5, but this number has to be odd, of course. So, for example, in this case, we will have 3 d5 plus 5 d5 is 8. So we have an overall even number of flavors under the fundamental of USP2. So there must exist an inflow that talks with the boundaries and solves the anomaly. So the 6D bulk, the D5 living on top of the O5 plus, can be seen as a 6-dimensional anomaly theory with a topological action that has a 5-dimensional boundary where the anomaly is localized due to anomaly inflow. No? So to cancel the anomaly in the 6D bulk must exist an eta invariant on this type. So we are like predicting the system of this eta invariant in this string theory configuration. This eta invariant was described by these papers, for example. Heuristically, this can be argued for a K-theory generalization of the Chen-Simon coupling, this Chen-Simon coupling that lives on the D5. We need to add the action of the O5 plus, but on the D5 already there is this coupling, and we see that for C0 equals 0 is 0. We don't have any inflow, but we don't have any anomaly. We saw it for C0 equals 0. We have an even number of fermions. But for C0 equal 1/2, we have that this is non-trivial. So let's go to the gravitational dual, where we will see that a puzzle arises. No? Let's take again this is like the overall story, but let's go to the gravitational dual, to this theory that we saw in the introduction. We have the NS5, the O5, and we saw that the NS5 span grab S2. The O5 also span an S2, sorry, a 2-sphere. So they span ADS4 times S2. And you can see it like this. This will be like the S2, like the orientifold. And as they share 2 dimensions, the NS5 is wrapped along the equator of this S2. So they divide both parts of this 2-sphere, and then in one part we have the O5 minus and the other the O5 plus. Here we have the same, the 6-dimensional gauge group, and on the equator, on this S1, we have the 5-dimensional with the ADS4 bifundamental half multiplet that we have before with the odd number of fermions. So we have an anomaly also in the gravity theory. Now let's compactify to 4D, like your usual construction. If we compactify, we see that this is mapped to an ADS4 end of the world boundary, where the orientifold is. And here we have the 4-dimensional gauge group and a 4-dimensional bifundamental half hypermultiplet. So we have odd number of fermions. Well, we have like the 4th homotopy group is not trivial. This is from Wittens. So we have an anomaly here. So we will need to have an anomaly inflow. But this poses a puzzle. Why? because because we need a 5-dimensional anomaly inflow that has to come from the ADS5, from the bulk theory. But for example, if we take empty ADS5 with the holographic boundary, we don't see any inflow. If there is an inflow, an anomaly inflow in the ADS5, it will impose an anomaly on the holographic boundary, and we don't have any anomaly. This is a way to see it. So this anomaly doesn't exist. So how we don't have a 5-dimensional anomaly inflow. So how is the puzzle solved? We will see that it's solved at the end of the whole brane. No? At the end of the whole brane, the gravitational dual, we have that the anomaly on the S1 has to be cancelled by the inflow from the disk. The boundary conditions that are Atiyah-Patodi-Singer boundary condition is that the S1 talks with the disk implies that the fermions on this S1 has to be antiperiodic. If we now dimensionally reduce this sphere, antiperiodic fermions give rise to massive field. So we don't have a 4-dimensional massless Hafifel multiplet, so we don't have an anomaly in the 4-dimensional, 5-dimensional picture. So a general conclusion from this section, and we will end, is that no matter how complicated we can make an end-of-the-world brane configuration in our 10-dimensional, when we reduce it to a 4-dimensional boundary of 5-dimensional ADS5, it must necessarily come out as free of most anomalies. No? Majority of anomalies that are not encoded in the usual Chern-Simons coupling of ADS5 that we saw in the second part, they have to be cancelled by themselves, these anomalies. So a general lesson of this part, the take-home message is that the structure of anomalies of any d-1-dimensional end-of-the-world brane in any quantum gravity theory is fixed on terms of the universal topological inflows that can exist in the d-dimensional quantum gravity theory. So let me conclude. We explained and we saw the SymTFT of a field theory with boundary, and we saw its symmetry structure. We broke SUSY at the end of the world brane, and we saw the appearance of anomalies. We saw that we predicted an eta invariant in a string theory configuration, and we characterized the possible topological couplings that we can have. Thank you very much.
Thank you very much, Jesus, for this very nice talk. Shall we have time for a few questions? You can raise your hand on Zoom or alternatively just speak up. Marcus, please.
Yeah, hello. Thanks for the nice talk.
Hi.
So one question I had, sometimes anomalies are not necessarily captured by massless degrees of freedom, but also can be captured by topological field theory. So if you include that possibility of not seeing the anomaly on the level of massless fermions, let's say, but on the level of topological phases, could that modify the story in some sense? I think the argument that you made, and like if you would have something non-trivial, then you would automatically generate an anomaly on the boundary, which is not there. That goes through. But in principle, the argument of not seeing any massless fermionic degrees of freedom is not enough to ensure that there is an anomaly, I think.
I mean, this anomaly is about fermions, massless fermions. Of course, we can have another type of anomalies, but then we will see them like looking at the topological couplings that we have also. No, I mean they won't be produced by massless fermion, but
yes,
they will be produced by these topological couplings. The point
absolutely
is, maybe I didn't stress it, but in this type of end-of-the-world branes, our bulk is the one of ADS5. So the topological couplings are very well known, are very limited. So any anomaly that we can engineer in end-of-the-world brane has to be cancelled by itself, by an inflow of some other anomaly in this end-of-the-world brane. Be this like a fermion anomaly or this other type of anomaly that you are mentioning. But I mean that this is like the the general message. This anomaly is about fermions. In the paper, we look at a parity anomaly. Well, it's also about, well, but I think that the story is general, yes.
Mhm. Okay, thanks. And maybe another question, if I
Yes.
may. You have it also in the conclusion slide, the connection between supersymmetry breaking and anomaly. So somehow it seems that the more supersymmetry you break, the more inflow mechanisms you will generate somehow. Is that what you would expect? Or is there a reason to expect that?
I mean, if we don't break supersymmetry, we don't have a lot of freedom to do things, no? It's like
Yes.
with system supercharges, everything is very constrained. Another thing I wanted to mention is that I briefly explained, but we also introduced these d5 primes and ns5 primes that also breaks the supersymmetry to force supercharges. They don't introduce any anomaly. No, it's only with this locally breaking of SUSY with the orientifold that we managed to get this anomaly. Also, for example, for the C0 equals 0, we don't get any anomaly. So I think it's related. I think it's related to the more freedom that we have when we break SUSY. We have more possibilities. Yes.
Okay, thank you very much.
Thank you very much.
Okay, any final questions for Jesus? Okay, if not, I think this is a very good time to officially end this meeting. So let us thank once again both our speakers of today for their very nice talks. And we will resume the seminar series in 2 weeks from now on the 12th of November with talks by Luis Garcia, and Gonzalo Villa. Thank you very much again for joining today. And once again, the Zoom meeting will remain open for a bit if there are questions that you would like to ask the speakers in private. Goodbye.